Okay, working on Advent of Code 2025, day 10. Let's see, large factory. Need to initialize it, no manual. The initialization procedure was eaten. Indicator light diagrams, button wiring schematics, and voltage requirements. Each line is a machine. Okay, indicator light diagram. Button wiring schematics, and voltage requirements. The lights need to match this diagram off and on. They're all initially off. Okay. Third on, fourth on. Can toggle by pushing any of the listed buttons. Each button lists which light indicator lights it toggles. And they're flipping, so when I push this button, it'll toggle 0, 3, and 4. This looks like it'll be some kind of bit manipulation. Check. Voltage requirements are irrelevant now and can be ignored for part 1, I'm guessing. Fuse total press is required to correctly configure all indicator lights for all machines. Okay, so I get the fuse total presses required, add them together to get the result. Alright, save the sample. Get my day 10. Let's copy yesterday's boilerplate to new main.com. It was 7. Again, we'll take the contents of the file for input and we'll output interface, which can be anything. I'll just say return nil. Alright, now we need to parse. I think I will create a type and a parser. Do I want to start with the bits, or do I want to see his leftmost first? This is 0, this is 1, 2, and 3. Okay. Should be 1 and 2, so this should be it. Toggle 0 on and 2 on, toggle 0 off and 1 on. Got it. Is int big enough for all of those? Let's check the input. Make sure I don't need an array for that. Nope. Okay. Store that as an int. And I will also store this as an int. And there are multiple buttons, so it's an array of int. And joltages, I'm going to ignore that for now. Some regular expressions to parse those. For everything between brackets. Let's double check that. Regex 101. This needs to be not close bracket. Looks like it would work because it was greedy. Or not greedy. And it's group 1 that will be found. All right. So I test for that real quick. try this, so make sure it goes the right direction. So this should be 14, 8, 4, 2. Actually, this is testing the regex, so we'll use a whole line. And that's what I expect, alright? Let's just run this and see what I get here. This should be an array, so it should have one element, and that should be this, I believe. Yep. Okay, passed. So now, function to get the light's value. Should I take the line or the value from the regex? I will say value from the regex. Start with a bit value of 1. Actually, let's use the index also. Let's do a bit value there. No, it'd be easier to change it every time. The light should be on. Take a bit value or tilt. Or bit value. And every time I want to shift it left 1. Alright, so we test for that. Let's see, this should be 14. Let's make this bad just to verify it fails. Okay. Good so far. What else do I need? It's the same type of thing for the button codes. Return everything inside of parentheses. So let's use this sample. So for this I expect 6 different strings to be returned, each a comma separated value. And let's try a test for that. Well, let's try in regex 101. So they're each a match, and group 1 is what's inside of it. Could probably do that without using groups. Could I? capture group 1. Value 0 would be the entire string including parentheses, so value 1 is what's inside the parentheses. And that's what I expect. Okay. But not value, string array. Expected 0 is 3. String array 1 is 3. So yeah, these should all work. Pass. Okay. You know what? I will have this take the entire line. I'll change my test. Find string submatch 1. Each found one will be an integer. Look through the found strings. Actually, it's a submatch, so okay. That's the actual string inside. Okay. Let's create another. How do I split a string? string and the separator. So and that's a string. Number string. Okay. Oh yeah, there's an error I can ignore. Okay, that looks good to me. Let's write a test for that. So 3 would be 2, 4, 8. Should be 10. Zero, 2, 4. 12, 5, 3, right. Let's pause right here just to make sure everything's similar. So turn in 8, 10, 4, 12, 5, 3. Okay. That's all I need to complete the puzzle, so let's parse puzzle. Parse puzzle required and buttons. This we need this lights. Parse machine. lights, get buttons. That's it, huh? Yeah, I'll get the lights and the buttons from the line and return to machine. How big are these lists? That's the furthest to the right. Oh man, that's not too bad at all. 200 columns. Probably just like 6 buttons. I could just brute force it, I think. Okay. It's been a while since I've done a puzzle like this. Start with nothing pressed. Do I go recursive? Do something just a little different. Value and depth. Okay. I don't just need the depth. Count of how many buttons are on. never be a reason to press one button twice. That would just cancel itself out. Start with 0 value, 0 depth, 0 presses. It's all off. It should return 0. Okay, I'm going to try two things. This is pressing depth button. This is not pressing depth button, moving on to the next button. Let's see. Okay, I need a value to indicate it's bad. I did not find a value. That will be -1. Off presses is easy, I just call the next one. On presses, I need to alter the value. So when that's called depth 0, this will turn on 1 bit. No, that's not right. Depth. XOR was the button value. Sort of flip the bits. And that included a button press. So if they're both invalid, I'll return invalid. If only off is invalid, I'll return on, vice versa. And we get down here, they're all both valid, so we need to return the minimum one. passed in the correct value, I return the total presses that were passed to me. So 0 would be 0. If I've ran out of buttons, return -1. If I calculate going on to the next depth, passing the same presses and the current value, so I didn't press this button, but I might press other ones. Then for the on value, I get the value for the current depth button, XOR it with the current value, and pass that along with the next depth and counting one extra press for the button I just pushed. So I'll return -1 if we didn't find the value. If neither way finds a value, I'll return -1. If I didn't find it by not pressing the button, I'll return on presses. Actually, I don't need this. If I didn't find the off, I return whatever on was. I don't care. If it's -1, that's fine. If I didn't return the on, I return off, whatever it was. That's fine. So they're both valid. I return the lesser of the two. And let's go ahead and make this an else. I like doing that because the conditions both have the same weight, you know. Rather than default to on, it makes sense to put them both in if clause. Let's see what happens here. Use parse machine. So we have 0, 2, 3. One press. How do I end a struct like that? And where do the array things go in front of the struct? It's an array of self-struct. Input an expected result, and there's going to be a comma in an array, even if there's no other element. Cool. What's the problem? Oh, too many. Add the index. Is it stuck? No. Huh, I wonder why it took so long. Okay, let's add the test from the sample. This should be 2. Second machine should be 3. And this machine should also be 2. tested. See if it works. Seven's good. Input 530. Voice. Break, be back. Okay, so I spent a lot of time on day 10, part 2. And I'm going to do a little bit different here. I'm just going to kind of go through how I did my solution and how it works instead of solving it in real time. Okay, if you don't remember, here we have same type of puzzle input. We can ignore the lights now. What we need to find is the minimum number of presses for each of these buttons to equal the output voltages here. It's like if you look at this, configuring the second machine's counter requires a minimum of 12 button presses. Press this button, 0234, twice, which provides 2 of voltage 0, 2 of voltage 2, 2 of voltage 3, and 2 of voltage 4. Press 235 times, which adds 5 to voltage 2 and 5 to voltage 3. And press 1, 2 once, which adds 2 to this and 2 to this. So 0 is done 5. Oh, sorry, that's wrong here. Here's the correct line for this middle one. Press 0, 2, 3, 4 twice. So that's 0, 2, 3, 4 is adding 2. 2 and 3 5 times. So 2 and 3 5 more times. And 0, 1, 2 5 times. So if we add up, we press 0 twice and 5 more times. We press 1 5 times. Press 2, 2, 5, and 5 more times. That's 12. Press 3, 2, and 5 times. That's 7. And we press 4 only twice. That's the 2. So how I solved it was using linear algebra and matrices. So this sample 0, 2, 3, 4, I have button 0. I put a 1 in the lines for 0 voltage, 1 and 2, 1 and 3, 1 and 4. Next button I put in values rows 2 and 3, then rows 0 and 4, then rows 0, 1 and 2, and 1, 2, 3, and 4 have 1s in them. And then the voltages go in this special column here for the output. So how this works is it's like a algebraic equation. Let's say button 0 is pressed V times, button 1 is pressed W times, etc. We can calculate the voltage using 1 for each press of button 0, 1 for each press of button 2, which is X, and 1 for each press of button 3, which is Y. That total should be 7. Do the same for all the other rows. So of course there's algorithms that math people have invented to solve these types of problems in a systematic way and reduce them to make them easier to solve. Generally, they involve creating a pivot value in each row, where it's the only value in that column and has a value of exactly 1. So if we solve the other columns, the effect of the joltage, we can use that 1 to calculate the exact number of times we need to press that button after solving for the other ones. Here's that example 2. We start by picking a pivot in the first column, place it up in the top left, and then we subtract this from any row with a 1 in it to get those values to be 0. Actually, they're usually referred to as multiplying by some value and then adding it to the row. So we would multiply this row by, or the values in this row, we take that out, multiply it by -1, and add it to each of these rows. So we can see that 1 subtracts from these 1s to get 0, subtracts from these 3 values to get -1, -1, and 0, subtracts from these 3 values to get 0, -1, -1, and take the joltage off of 7, or 2 minus 7 is -5. So then we move on and pick a pivot value in the next column. And what we do is we swap it so it's in the next row below the previous pivot. So we end up with a staircase here of 1s, where we have 0s below each pivot and 0s to the left in every other row below. So here I take, this is the pivot, swap it up here, that shows this, and then the only other row with the 1 is this one, so I subtract this again from here, so 1 minus 1 is 0. Or 1 minus 1 is 0, -1 minus -1 is 0, -1 minus 0 is -1, and 1 minus 1 is 0, and then 0 minus 5 is -5. Moving on, there's no acceptable pivot remaining below the previous pivot in column B2, so we move on to the next column. Here I could pick any of these 3 values, but if I want to use one of these, excuse me, first I need to multiply the row by -1. That does not change the value. If we go back and look at this is the same thing as saying -1Vx minus x minus y equals -7. But here I'm picking this as a pivot, and so I have to get these 2 values to equal 0. To do that, I add this row to these. So 1 plus -1 is 0, 0 plus 1 is 1, -5 plus 5 is 0, -1 plus 1 is 0, 1 plus 1 is 2, and -5 plus 5 is 0. And finally, in the last column, in addition, any rows with all zeros should be at the bottom, of course. It just flows. But here I pick this as a pivot, and I subtract it from this. Subtract 2 times this row from this, gives me all zeros. So this is called row echelon form, where all rows consisting entirely of zeros are at the bottom. The first non-zero entry in each row is to the right of the pivot in the row above. So this one is to the right of this one, this one's to the right of all these, and this one's to the right of all these. And all entries below the pivot are 0. This method for doing this, I believe, is called Gaussian elimination. So already it's simplified. I could tell this joltage doesn't matter. And you might think that's strange, but how it ends up is the way the puzzle's set up. It doesn't matter how we push these buttons. If we end up with the right joltages in these rows, this will always be the right joltage. And we can also see this row has a 1 here, but 0 joltage, so we know this won't be pressed ever. So now what we're trying to do is get rid of these values above the pivots, so the pivots are the only values in that column. So here I start from the right. I take this pivot and I subtract this row from these two rows to get zeros there. I'm also subtracting 0 from the joltage, but that's not affecting it. These do become 0 though, and this 1 is the only remaining value in this column for button 4. For the next higher pivot, I do the same thing. I subtract this row from row 1 to get 0 in that column, and that lowers the joltage from 7 to 2 because I subtract 5 from it, and makes this 0, so 1 is the only value in this column for button 3. There's nothing else I can do. This row already has zeros above, and there's nothing above this pivot. So now it's in what's called reduced row echelon form. It's the same, it has all the qualities of row echelon form, plus all pivots have to be 1, and there's zeros below and above every pivot. So if we take this and convert it back to what would be a puzzle input, this is the original puzzle. I'm not sure we arranged the rows and joltages, so the lights will be something different. I don't care, it doesn't matter for the second part. And then we would have button 0 affects joltage 0, button 1 affects joltage 1, button 2 affects joltage 0 and 1, button 2 affects joltage 2, and button 3 affects joltage 3. We also have new joltages because we simplified. So you can see this is a lot easier to solve than this, even if you want to use brute force. So what does this mean? So now we have 4 pivots where that is the only value in the column. If we set those joltages, I call these the dependent buttons. Once we set the joltages from other buttons, we can use the remaining joltage to calculate the exact number of presses. So I don't have to iterate over these buttons. I just have to iterate over button 2. So I call them variable buttons. So if we look at the initial joltages that were affected by B2, they were 7 and 2, and keep track of the maximum number of presses for that button, then is 2. Because if I press it 3 times, the joltage would overflow from the initial matrix I created. So we permute all the possible ranges for the variable buttons. Make sure the joltages are positive. Or actually, that's not what we do right there. We just got to permute all the possible values. Then we can calculate the required number of presses for the dependent buttons one at a time. So there's only 0 to 2 times we have to press button 2. So here I take each of those 3 options. I gray out column B2 because I apply this being pressed this number of times to the joltage. So here pressing 0 times, it remains 2, 5, 5, 0. If I press this once, I take away from the required voltage for the other buttons, say from 2 to 1. And same here, I take away -1 and make this 6. So pressing button 2 means I have to press button 1 every time I press button 2, if that makes sense. And pressing 2 times, it looks like this. So if I look at pressing button 2 0 times, this is what I'm trying to figure out. Now I know I need to press button 0 is the only remaining value in this row for joltage 0, and I have to press it 2 times to get that. Likewise, I have to press button 1 5 times button 3 5 times, and button 1 0 times. So each one of these is now the exact voltage I need to solve the puzzle. Afterwards, I need to make sure, all the voltages are 0 after I press that number of times, and I cannot press a button negative times. That's the only thing. So I go back to where I have the -1 here. I guess that doesn't matter, because I can always press this more times to help it out. So if I press it one time, likewise, I've subtracted that press from these voltages. And now I know I need to press button 0 one time, button 1 6 times, button 3 5 times, and button 4 0 times. It's a valid solution with 13 button presses. The previous one was a valid solution with 12. And if I press B2 2 times, then I gotta press this 0, this 7, this 5, and this 0, so that's a total of 14 presses. So we can see there the first one with 12 presses was the least. And if we look back at the puzzle, that is exactly what the sample says. Press 0 2 3 4 twice. That's button 0 twice. Press button 1 5 times. That's what I have. And press button 3 5 times. That's what I have. And 4 and 2 are 0. So that matches. Now I decided to use integers for a couple reasons. I like to, as I'm going, be able to print out my matrices and not have like long strings of digits or have fractions in the results. Keep them easier to read. And it made it easy for me to follow so I could completely understand what was going on and reason how they equated to the problem. 1 means I press the button once, and -1 means the additional voltage must be made up by pressing a different button, etc. And it made it a lot easier to figure out what went wrong when I had a bug in my code. Now, using integers does have some problems. All the well-defined algorithms for doing these sorts of things use fractions or floating point numbers. So if I end up looking for a pivot in a column and there's no 1s remaining, it breaks the Gauss-Jordan algorithm. It could be handled by using floats. I thought it'd be slower and there might be routing issues. And so if I have to skip a value that's not 1 or -1 for a pivot, it might be not completely optimized. I might end up with more variable buttons I have to permute and fewer dependent buttons. I gave up guaranteeing an optimal solution and complying rigidly with the mathematics algorithms and definitions for reduced to echelon form, etc. But I did look for a potential pivot in other columns. It breaks some of the rigorous mathematical definitions they have, but just by reordering the variables, it doesn't really matter. Everything is still equally solvable. I get why a mathematician wouldn't want to see, they'd rather see 4x minus 2y than plus 3z than 4x plus 3z minus 2y, because they like to keep their letters in order. But if we keep track of the column swaps we do, we can't just rearrange them at the end for the solution. That's exactly what I did. So I think there's other possible optimizations I could make. What's really important is having columns with the most columns possible with a single value in them. Those are dependent. I don't have to permute those. I can just calculate those after I permuted the variable columns. I could look at all pivot rows and try each one first. I could permute all the columns. Maybe it'd be better to use columns with fewer ones in them. Sort the columns by how many ones are in them. That would mean I would be less likely to get a bad value because I would have fewer row operations every time. I could look at each possible pivot value independently. Maybe I try each swap each column, try for the next pivot. So I try each of these three is the pivot first for this spot. Then I try each of these two for this spot. Try each of these four for this spot, etc. So I would have like 216 combinations I would have to check. But almost, because they affect other values. So when I pick this pivot, it changes these values. So I might have different number of pivots in that case. Maybe I could represent it as some sort of graph, like, oh, this, if I pick this, it's going to affect this also. It might be in a good way, like this subtracting from this creates a 0 here, but it also adds a 1 here. I could look at each possible pivot out of every single one in the whole thing. I could choose that and move that row. Like if I pick this one, I would move this row, swap these two rows, and then swap these two columns so that this one ended up here. If I pick this one, that's 15 choices for the first one. If I pick this one, I have 11 choices for the next one because I'm not looking at this or this. But let me see, actually it greatly decreases the size of the graph. Instead of a 5x5 area I'm looking for pivots, now I have a 4x4 for the second step, then a 3x3, then a 2x2, and finally one possibility for the last one. So that'd be approximately 825 cases I would have to explore, trying each pivot individually. I have ideas for making it more efficient, just keeping track of swap columns, what have you, but anyway. I'm going to link to a couple of sites and some good videos. It's this linear algebra toolkit where you can input a matrix and it will do the operations and show you results after each step. And Wolfram Alpha has a similar thing. It doesn't give me all the steps. I think, yeah, I might have to be pro for that. Yeah, it wants me to go pro. But I do have a function there to convert my matrix to this form that it takes as an input. If you want to try it out. This linear algebra toolkit came up with the same result I got, it looks like. So anyway, let's look at my code. I have this all in one file if you want to try it out. I also have it in my repository under working part 2, where I separated out the code into a few different files. I have these variables explain and output each, so when I run it, I can output each. Just basically gives me a couple little extra text here showing the line and the actual presses from the optimal solution. Output each actually shows all solutions with the minimum presses. And my solve line just takes one puzzle line, calls the functions to parse it, does the recursive reduction to reduce row echelon form, and calls my solver. The matrix struct is pretty simple. I have the rows and column counts, an array of ints, one array of ints for each row. They also maintain the original rows and columns, so as I do swapping, I can always see what the original row was for that and column, and then maintain the maximum presses for each button. I thought about possibly reducing that as I go along, because sometimes intermediate steps can give you better results. Like if I subtract 5 from 7 of one joltage row, then any other buttons that affect that would have that new maximum of 2. I just have to ensure that they're all positive or all negative. I could also add a minimum presses, so if there's one value that's positive in that row, all the other values are negative, then I know I have to press it at least that many times to get the joltage, or vice versa. If that value and the joltage are negative, other values are positive, I know I have to at least press that button enough times to get it that negative. A pretty simple operation is to swap columns. I swap the original column value in the array and the max presses, as well as the values in the matrix. New matrix just creates the data and populates the structure. Simple functions to get and set given a row and column. I have a function to add the source row to the destination row using the specified factor. So if this is -1, it'll subtract the source from the destination. I can multiply a row by any factor itself. I just use this for if I have a -1 in that pivot column, I can multiply the whole row by -1 to make it a 1. And swap rows, pretty easy. I just swap the arrays for those rows. Okay, one important thing I wanted to do, just for visibility and understanding, was to keep track of the actual presses. I don't see many solutions that do that. A lot of them use deep recursion and things, but don't track which button was pressed how many times. I want to do that. I give the total presses and how long it took. I don't think I actually specify that now. Now here's the main function to do the reduction. And a lot of places in here, if I have that explain flag set, I do a little extra printing, as you can see down here. Say, oh hey, here's the initial matrix, here's the Wolfram value. I have it pasted in the Wolfram site, and that's what it looks like. So here I have button 0 through 5, and row 6 is the joltage. The max presses for each of the buttons. The values in the matrix, and then the row and the original row. So here I'm swapping the good row 3 to get this pivot at the top with pivot row 0. And you can see it's still row 0 in the matrix, but the original row was 3. Add 1 to row 0, add row 1 to row 0 with a factor of -1. See, I'm kind of doing the second part of the reduction right away when I find the pivot. So I'm subtracting this from this, so this is the only value in that column. Then I'm adding it to row. Oh, now I've selected the pivot here. I think adding row 3 to row 2 with factor of -1. Initial after swapping, after adding row 1 to 0, just after adding row 3 to 2, well, that doesn't make any sense. Adding row 3 to 2. How does this change? Oh, yeah, I've already figured out these pivots all the way down here, so I'm adding this row to this row, which gives me the 0 here and the -1 with the factor of -1. Yeah, I'm done. Now swapping columns 3 and 4. Put this 1 first over here. And the advent of code sample says optimum presses is this. And that's where I see 4 possible options for the optimal presses, and this is one of them. So here I give the row and column initially this 0, 0, so I pick the pivot in the top left corner. It exits if we're past the rows or columns. Keep track of if they're all zeros, which is fine, I just move on. Or I find the good row. -1 means there's no good row. I go through starting at the pass row, looking down, look for a 1 value, set that as good row and break. If I find one, same for -1, I go ahead and multiply the row by -1 and then set that as the good row and break. And I keep track of whether all zeros or not, because I could have a value like 2 in there, and I don't want to leave that there. I want to swap columns so I can get a good pivot in that column if I can. So in the happy case where I have a good row, I swap if it's a different row. I found the 1 in. Fix up the zeros below, adding row with factor. I'll go ahead and change this to say I'm adding up. Keep it the same format. So I'm adding like row 1 down to row 2 with factor blah blah blah. Like row 1 up to row 0 with factor blah blah blah. So these are the 2 parts that make sure this is the only value in that column. And when I'm done, I move on to the next row and column. If they're all zeros, I just add 1 to the column. If that's the case for, go back here, right here. That'd be the case here where they're all zeros. So I go ahead and just move to the next column, look for another pivot. If this were 2, I would go and find, I would find a 1 in a future column and swap that column with this one, so this would be the pivot. And that's what I do here. If there are no future ones, it just returns, and that's the end of it. There might be columns and rows with non-1 values, and I think that's fine. So for solution, I keep track of the presses and the total presses. I want to keep track of all the possible solutions. And so I have a sort function, so I can sort them with minimum presses first. Not sure what that is. So here's the main solver. It returns an array of possible solutions. I created a list of dependent buttons, making the initial size 0, but allocating enough space for all the buttons. And same for the index of the joltage that button affects. If it's a dependent button, remember, it's going to be one of these with nothing else in that column, so it still affects this joltage. And I keep a list of the variable button indices. So I start looking at each column. I find the row with the 1. Record the first one I find. Oh, if there's more than 1, I break and say there's no 1 row. So it's a variable column. X equals 1. So if I find a 1 and there's not already a 1 row, I set the 1 row to that. If I find a 1 and there is a 1 row already, I say nope, there's no 1 row, and I break out of the row loop. So if it's not a 1, a 0 is fine. I don't do anything, I just continue through the loop. If it's a value other than 1, I say nope and break. So if it's not a single 1 in that row, add it to the variable buttons. Otherwise, add it to dependent buttons and record the joltage row that that dependent button affects. I have a list of ints for the variable buttons. That will be the rows each variable button affects. So I initially create the list of joltages for each one. But I add the variable buttons up here. Variable buttons is just a list of indices. Create the joltages array, and then I look for any non-zero value in that variable button column and add the row index to that joltages array. And that's what that is. So now I want to permute all the variable buttons. Start with an array of presses that's initially 0, keep track of whether I'm done or not. I was pretty happy with this function. What it does is it permutes those buttons. So let's say these two were variable buttons. It would, and this max presses was 7 and this was 5. I would start by increasing this to 1, then 2, then 3, then 4, then 5, then 6, then 7. When I permuted 8, it'd be like, oh, that's too high for the max presses. Set to 0 and permute the next variable button. And when that goes past its end, and then the next time through, this will go back to 1 through 7, And once this gets past its max, because it's the last variable button, it would end the permutation, set done permuting. So I like this because it keeps track of And so the way I do it here, I keep track of the current presses in this presses array for the variable buttons, and that lets me maintain that list of the presses for each button at the end for my solutions. So this is the function, let's say permute, and I just kind of record a total permutation count here, just how many total presses I have to look through. I don't actually do anything with it, except make the solution array of that length. So if every single possible combination of the variable buttons results in a good solution, not necessarily a minimal solution, I will have that many solutions in this array. And then I loop through while I'm not done permuting and call that permute function after the loop to move on to the next one. If that overflows the final variable button, that will set this flag and it will not do it again. So for each permutation, I need to initialize the voltages. I clear the dependent buttons to 0. And for the variable voltages, I look at how many times they were permuted to be pressed and multiply that by the rows to set the voltage in this array. Now everything remaining should be a dependent column with a positive 1 in one row. So I make sure it's valid. What's this? Voltages are less than required. Okay, I compare it to the original voltage. So if it overflows, just pressing those variable buttons overflows the target voltage in any of the rows, I don't need to calculate the dependent buttons. And I continue through the loop, permute another value, etc. So each of the dependent buttons remaining should be a one-to-one relationship with a voltage in that value. So I look at the voltage in my matrix for the puzzle, subtract the voltages from the permuting buttons, and that's how many times I have to press the dependent button, which will have a 1 in that matrix cell, and that will increase the voltage by the same amount. Now I make sure they all match. It's possible there's variable buttons that, or voltages that are only affected by variable buttons. In that case, they may be less than, so I just double check, look at all the voltages from pressing all the buttons in that presses array, make sure that they match what's required. Skip if it's not valid. So I have a solution. I just calculate the total presses, copy the array of presses to my solution, because this gets updated every time through the loop. And here I reorder the presses array, which goes by the final matrix, based on the original column, if I had swapped it to columns sometime. And I append it to the solutions. I sort them and return it. Here's my helper, just a bunch of code for parsing the puzzle lines, turning the matrix into a strings for display. What I do is I calculate each cell and I kind of make it as condensed as possible. I want to update this to have that line like a lot of videos have. And there's for displaying the Wolfram string. If I go to my sample test, this is the sample 2. And you can see it looks, I think, just like my presentation. 1 over here, 1 down here, and then button 2 is 1, -1, and that's 255. Other than I rearrange the columns to keep these in a diagonal pattern here. So this is really original row 2, or column 2, sorry. But I fix those up when I record those and save the presses for the solutions. If we look at sample 1, see what that looks like. I find 4 optimal solutions, one of them being the one specified in the Advent code page. Here I have 2 variable buttons I need to permute. One goes from 0 to 4, the other 0 to, or 1 from 0 to 4, which is 5 possibilities, 1 from 0 to 3, which is 4, so there's 20 total things I have to check here. And sample 3 from Advent code. Find it's the same optimal presses said on their web page, 11 presses and the same button combination. Here I end up with 3 empty rows, which is kind of nice. 3 dependent buttons and 1 variable button that only has 2 voltages and effects. If we look at some from my actual input, which were difficult, here's a good one that took originally, I think this is one that took like 13 seconds before I add the ability to swap columns. Now it's pretty much instant. It was 10 voltages and 13 buttons in this one. Find the optimal solution. 1 1 1 1 1 1 1 1 1. See, something I could optimize here. I was starting to do. This is a 2, so it can't be a pivot, but all the values are even here, so I could find. Look at each row and find the greatest common denominator and divide by that. So this would become a 1 and a 4. Then I would subtract, a multiple of that, or add a multiple of this, positive or negative to each of these, zeroing out the rest of the values in this column and leaving me with, 3 variable buttons instead of 4. But yeah, before I swap the columns, I got stuck right here with 5 variable buttons, and that was taking 13 seconds. So what I do here is I swap columns 8 and 10. I find, oh, here's a 1. I'm going to swap columns 10 back to column 8, and then I'll be able to use that 1 to form a pivot by multiplying the row by -1. me have a look at my code if you're having any kind of trouble with part 2, and even if you don't want to do something similar, just have a lot of explanations here, and you can show you the optimal key presses. So maybe you're doing some kind of other algorithm, bifurcation, whatever, and getting something just a little off. This might help you be able to diagnose what that is. And after doing that, I was able to complete day 12. I was all done. Advent of Code 2025. Hallelujah.